I do realize I walk away from the mic every now and then. So there'll be times on the video where you can't hear me at all, right? But I'm trying to be conscious of that to get back and maybe say what I just walked away. I've been recording 2 years without moving away from my desk at all, right? I'm not used to it again. So let's take a look at this limit. The limit, well, we'll do an easy one first, right? And then I'll do 2 of these. Are you going to be asked to do any of these on your test? No. So, but I need this. I needed this definition to do that replacement function piece. I need this definition to show you that limits don't exist in cases. I need this definition to show you more complicated limits later on, right? But I'm not asking you, you're not responsible for this, so if it's really freaking you out, do you understand, does anybody kind of understand the dartboard thing or the target thing? You feel like it's a little bit more understandable than for every epsilon greater than, right? For every epsilon greater than 0, there exists a delta greater than 0 such that 0 is less than the absolute value of x minus c is less than delta, implies absolute value of f of x minus L is less than epsilon. That doesn't make nearly as much sense as me saying, if I have a dartboard or a target, I can find a bullseye such that if I never shoot outside of the width of the bullseye and I hit the target, so you can see that strip of the target as wide as the bullseye. If I guarantee to hit that strip, then I get the limit, right? That's easier to think about. And hopefully what I show you today will make you go, oh, I get it now for sure. So what's our limit of let's say 5x minus 7 as x goes to 2? What is that limit? Yeah, so this one I can plug right in, right? So 5 times 2 is 10, minus 7 is a 3. Now let's see if I can get that into my translation, right? This is equivalent to, or if and only if, or the double implication arrow. This is exactly the same thing as what? For every epsilon greater than 0, there exists a delta greater than 0. I want to fill in this piece. What should I put in for C? Yep. And what's f of x? Yep. And what's L? Yep. So 5x minus 7 minus 3 less than epsilon, right? So I can simplify that a little bit, right? For every epsilon greater than 0, I better be able to find, for every target, I better be able to find the radius of my bullseye such that 0 is less than the absolute value of x minus 2 is less than delta, implies 5x minus 10 is less than epsilon. And you can kind of see it already, right? You can cheat it. We can cheat it already. I'm going to use a delta as epsilon over what? Does anybody see it on the board? You can kind of see it from here. Yeah, epsilon over 5. You can see I'm going to factor out 5 here, and I'm going to get an x minus 2, right? So there's my x minus 2 piece. Right? You see that? Kind of. If you don't, it's okay. So I'm going to let epsilon bigger than 0 and pick delta equal to epsilon over 5. Just because I know the answer. When it's linear, it's always going to be epsilon over that slope, absolute value of that slope. Assume 0 is less than the absolute value of x minus 2, which is less than delta, and show that the absolute value of 5x minus 10 is less than epsilon. I want to show that that point hit the board. I want to show that when I got really close to the x I wanted, the y I wanted to have. And so you see it, right? This is 5x minus 3 I'm sorry, 5x minus 7 was the original, was it? Yep, minus 3, and that's 5x minus 10, and then I can factor out a 5, and you can see that absolute value of x minus 2 is less than what on the page? Less than delta. So this piece I got is less than 5 times delta, right? The 5s are the same, right? You agree here? These 5s are the same, right? So that part's still equal, but this part is less than delta. So now this is 5. This is less than 5 times delta. There it is, 5 times delta. So what did I pick delta to be? Epsilon over 5, right? And so I got my epsilon. So I got my epsilon is greater than the function minus the limit. The arrow I shot hit the board between the width of the bullseye, and it didn't miss the board because with an epsilon. And then I shrunk the board down, right? When I shrink that board down, I've got to hit the limit. I got to hit the bullseye. All right, let's. Yeah. Say it one more time.
To find delta, you have to divide the epsilon by y.
Yeah. So really, what I did when I did this problem in my head is I did this work first. I did this work first till I got down to a delta, and then I realized what I want to make happen is I want this 5 to cancel, right? And so, and that's what. And at that point, I knew I needed an epsilon over 5. All right, let's see. Let's hope my app will make it all click, okay? So I'm using a program called Geometer Sketchpad. You can find this on GeoGebra. If you search for epsilon delta definition of a limit on GeoGebra, you can find it. But this is the one I wrote, so I like to use this one. This program's not free. Where are my, don't tell me. Oh, it's in downloads, I think. There it is. So what I'm going to do, you can see here I've got my my target represented by this B value, so that's my epsilon, and then my delta is here, right? So I could change either. But notice once I pick my delta, once I pick my bullseye, if I shrink down the dartboard, it's proportional, right? Yes, you with me there? Okay, so I want to just change my function. What did I have? 5x minus 3? No, 5x minus 7. And I was supposed to get a height of what? As x goes to 2, right? Right. And so I should have got an answer of, help me. What did I get? 3? Yes. All right, so there it is. Right? So I've got my, I'm trying to find, I know the limit is 3, right? It's obvious, yes? So I've got my x and y at 2, 3. But I'm trying to show you this dartboard here. So notice, remember what I said. I have to make sure I don't consider any part of the graph or the bullseye left or right of my constraint, yes, of this width, yeah? You with me? Okay, now notice, look at the function on the dartboard within that width. So let me see if I can do, I'm going to cheat a little bit here, sorry. I need a point here, and I want to do Oops, sorry, give me a second. Here and here, I want to create perpendiculars. Oops. Perpendiculars, parallels, sorry. Construct parallels. So there's my restriction, right? There's my restriction. Yes? Now, I'm only considering the function that's in between there. Now, what did I pick? Epsilon over what? 5. So I've got to change this down. This is about epsilon over 3. So there's my epsilon over 5. Closely, right? Right? 1, 2, 3, 4, 5. Yes? Look at the function now that's between my bounds, my gutter guards, right, and bowling. Do you see that the function is completely on the dartboard? You see that the purple part of the function is now so if I'm shooting at it, I have to hit the function. But I can hit it anywhere between these lines. I couldn't hit it here, right? Mm-hmm. But since I'm on the dartboard, I'm on the target. When I shrink it down, bang, I hit the bullseye, I hit the limit. Good at all? Question? So, epsilon is the radius of my bigger circle. Delta is the radius of that bullseye. If I pick the right delta, the function I pick, right, the function will remain on the dartboard. Thank you, Dr. Early.
Thank you very much. Thank you.
Say again? Yes. Yep.
So is the rest of epsilon not considered the start?
One more time for me. Say it again.
So it's only correct if it's at delta. It's not correct when it's in the whole epsilon.
Yeah. So if I pick the wrong delta, I think, Joanne, I think this is what you're asking me. So, but if I pick the wrong delta, right? You see here now, I pick the wrong delta. In between, remember I have the boards up, stopping my arrows from moving outside, but couldn't I still hit here? You see my function is there. Like the function is like a magnetic attractor for my arrows. So I just said I have to hit between, right? But I couldn't hit here. And what happens if I hit here and I shrink down the dartboard and I miss the dartboard? So I have to find the delta that works. And the delta that works will say, I'll be as close as I want to see, right? As close as I want to see, and still that purple piece that's there has better hit the board.
Okay, so the whole complex, like statement thing is ugly.
Yep.
So, do you have to memorize all of that to understand how to do the with the class?
No.
Okay.
No.
So it's just like the overall concept of the statement. You have to
Yes, I want you to get understanding more than I'm using this thing to get you to understand. If you understand this concept of the target, then you've got what I want you to have. If you further understand the epsilon delta statement, great. If you're a math major, you better. If you're a computer science major, the rest of you don't break yourself up.
Yeah, I guess for further calculus classes, that.
Yes. All right, let's take a break. Let's come back at 10:15, okay? Oh, graphical limits a little bit more. We did already, but I really want to talk about when do limits not exist, and then I want to do the secant tangent problem, okay? So this is still 2.2, but the main question I'm asking now is, when do limits fail to exist? And there's basically there's three answers. So we'll have either a jump in the graph, an unbounded, or an oscillator. I forget how to spell oscillation. How many, somebody help me. How many C's, how many L's? Can anybody spell? 2 L's, right? So the funny oscillation one, and it's a joke, right? I go down to my grandmother's dead, but I go down to my grandmother's basement, and there's that light bulb with the string. Does anybody remember seeing that in their grandparents' house? Then you pull the string and the light goes on, and you pull the string and the light goes off. And if I do this an infinite number of times, it's the light on or off. Infinite number of times, is it on or off now? It's off, because it burned out. But it's an oscillator. I can't tell where it's going to be on or off. Right? So I'm jumping between two heights, right? Can you see the heights of the functions jumping? And what about the formal definition will fail it? But, so can you see this oscillator? So like the famous one of all is f of x equals sine of 1 over x. This is such a beautiful, beautiful function. We know sine is at most 1 and at least -1, right? And so this thing is doing something like that. And so it's oscillating, it's going like mad at 0, going mad fast around the circle. So jumping between heights -1 and 1, right? If you could think of this as the frequency, you remember doing my trig students from last semester, my pre-cal students, we talked about frequency, that B value, yes? That B value, as that B value gets bigger and bigger, it's going around the circle faster and faster. Think about 1 over x, as x is going to 0, it's getting very, very large, very fast. So the thing's going crazy around the circle. Question?
What does underjump, what does that say?
Unbounded.
Oh, okay.
Like positive or negative infinity. Sorry, thank you. Yeah. So here is my dartboard. Here's my bullseye. Do you see how it fails? The dartboard, the target is that green circle. Remember, for every single target I want, right? But what's happening outside of the target? The function is happening outside of it. You see? There's some function outside of the target, right? So I'm missing the dartboard at that point. In fact, it has to work for everyone, right? It has to work for every single dartboard I pick. No matter what delta I pick, right? You see it? No matter what delta I pick, there's parts of the function that are off of the board. Doesn't hit the bullseye. It's obvious when you think of the switch. Is it on or off? You can't tell, right? Actually, Edison, I grew up in Jersey. Edison, his lab was there where he invented the light bulb. His original light bulbs still work. they're not changing them, they still work. So why is it that ours burn out?
So, even when inside,
Yeah, but why is it that they really burn out?
Because companies want us to buy more.
Money,
They're
money, money.
consumerism.
Money, money, money. Unbounded, right? Let's look at an unbounded one. So like f of x is 1 over x, right? And of course, where's my interest and limit there? Where's my limit of interest there? At what x value? At 0, right? So, and again, you can see the function's going either to positive infinity if I approach from the right, negative infinity if I approach from the left. But if I pick any single number as my limit, right? Let's just pretend I pick 3. That dartboard fails. It's easy to see that I can pick a dartboard that will miss that number that I say is the limit. Right? Does that make sense? Well, you say, well, it says for every epsilon greater than 0. So can I pick the epsilon real big so it gets that point? Yes, but it has to be for everyone, so I have to be able to shrink it down as well. Right? So oscillators, unbounded, and then the last one is jumps. That one's easy. I'll do my jump here. I like f of x equals absolute value of x over x. So if I put a positive number in there, the absolute value is useless, right? So I put 5 in, right? So I've got 5 over 5, which is what number? 1. Okay. If I put negative 5 in, the top number turns back to positive, but this one stays negative, so now 5 over negative 5 is negative 1, right? So this one's got a jump in it. And my graph looks like this. And this one I do put in my calculator, right? Remember, if you see a function that you've never seen before, put it in your calculator, right? It will really help. And where am I interested in the limit, of course? At what x value here? 0, yep. So I know my limit as x goes to 0 from the right of f of x is 1, right? If I'm walking towards 0 from the right, I'm at a height of 1. Do I care about getting all the way to this point here? Do I care about getting to 0? No, because the limit says 0 is less than x minus c is less than delta, right? I don't care about actually getting there. I want to be able to make a prediction before I get there. Then on the other side, my limit is negative 1, right? So the limit as x goes to 0 from the left is negative 1. Right? And you can see me walking again. I'm walking toward 0, right? I'm walking toward the origin. And I want to say, can you guess my height? And you can, it's negative 1, right? So, but the problem is, they don't match. They have to match left and right, right? So we say that the limit as x goes to 0 of f of x does not exist. I hate the fact that the web assignment will have you say equals does not exist. Because the equal symbol only means numbers. So, but a little bit of freedom there. Whoever designed it is not a real mathematician. Probably a computer scientist. Okay? So DNE does not exist. And of course, you can see the formal definition fails easily because of what? Because of what epsilon? What epsilon fails? Give me an actual number for epsilon. Well, epsilon greater than 0, right? So what'd you say? No negatives, right? Epsilon's got to be a positive radius. 0.01? Sure. I'll go point five. How about 0.5? So a radius of a half, right? So a half up and a half down. Is the function, no matter what bullseye I pick, is the function on the board? Is the function on the board? No.
It's when the epsilon works, like when that whole statement will work, the epsilon can be any number.
It has to be every number. For every epsilon, for every single dartboard, for every single target. I have to find a delta. But if the epsilon piece fails, why bother looking for a delta? So in homework 2, graphical limits, you'll see a problem like this. What is f of 3? And my tick marks are units. What's f of 3? Yeah, 2, right? F of 3 is this point, right? At height of 2, right? What's the limit from the left? Yeah, so the limit as x goes to 3 of f of x is 1 from the left, right? What's the limit as x goes to 3? It looks like 5, but it's 3. From the right, what's the limit? Also 1. So does the limit exist? It does exist. It's 1. Why don't I care about the 3? Why don't I care about this value? Do I care if there's a hole in it? No. Why don't I care? Why don't I care? I don't care about getting to C. I care about getting really close to C. From the left and from the right. Within delta, right? Within a radius to the left or a radius to the right. As long as I can make my prediction, I don't care about getting to C. In fact, what's interesting is when I actually get the limit, I shoot the arrow, what happens to the arrow? When I actually hit the limit with my arrow, right? 500 feet away or whatever, right? What happens to the arrow on the board? It goes through it. It goes through it perfectly, right through the center. Because I don't care if there's a hole in the board or not. At the center. Sometimes some boards will have the hole back, right? Then the arrow will stay. But if it's a board like this one, it will go right through. And why am I allowing that to happen? Because I'm not going to actually get there. I'm going to make the prediction before I get there. Nice. Here comes our dynamic. So this is 2.1 I'm talking about here. So that's it for chapter 2. I think there's more to do in chapter 2. I think I have to do a squeeze theorem, but I'll do that Tuesday. There's no homework on the squeeze theorem. The squeeze theorem will come from past problems. I did post, you are not taking chapter tests. You're taking a midterm. So your midterm will be chapter 2 and chapter 3. I'm gonna give you all of my chapter 2 tests for the past 4 years, all of my chapter 3 tests, all of my midterms. So you'll have plenty of things to practice, okay? So the squeeze theorem problem from 2.2, the website doesn't even make them, so I'm going to give you those problems in my review packet. All right, let's do this thing. What time are we done? 11:15? I want to leave early today, if that's okay with you. Oh, I'm recording that. You didn't hear that. I have a class at 12, but I just have a couple of things I have to do before my next class. So we're talking here about the secant tangent problem. And I told you about this. This is the average rate of change and the instantaneous rate of change, right? This is me driving 10 miles in 1 hour. 10 miles per hour is my average rate of change, average speed. But when I got hit with a speed camera, right, at that 1 millisecond, that 1 nanosecond, I was going 50 miles per hour. Okay? So, yes, I drive fast. But the idea here is we want to be able to calculate a slope at one single point, right? And that is exactly our derivative. So we need a couple of things. We need to look at our secant slope, right? So m is what? y2 minus y1 over x2 minus x1, right? You remember doing this delta y over delta x kind of thing? Yeah. Please tell me my chair goes up. That's it? Damn it. Oh, there's the high chair. I need a high chair. So I want to change my notation a little bit here. I want to change this to f of, right? And I'm going to change, so it's f of x sub 2 minus f of x sub 1, right? So the subscript simply meaning 2 points, right? The first x point, the second x point. Yes, you with me? So I'll start with a nice easy function. Let's say x squared. So this will be x sub 1 and this will be x sub 2. And this is, so my first point, right, is x sub 1 f of x sub 1. And the second point is x sub 2 f of x sub 2, right? Are we okay here? I'm not confusing anybody, am I? And there's my secant line, right? Right, we okay here? And so I want to rename my points as x and x plus h. This is my notation I prefer to use. The book will use delta x instead of an h. But I don't like the delta x. The two symbols, the delta and the x, kind of, it gets confusing, I think. I want to use a single letter between x and x plus h. So what's the distance between the 2 points? How far are those 2 points away from each other on the x-axis? How far is this? Yeah, h, right? So my secant slope now becomes f of x plus h minus f of x all over x plus h minus x. Make sure you're with me there. You can see I replaced all my x sub 2's with x plus h's. Right, my x sub 2 became x plus h. Right? And my x sub 1 was just x. And of course, that downstairs simplifies, doesn't it? So I get f of x plus h minus f of x all over h. And if you have me for pre-cal, or if you recognize it, you see the difference quotient. This is the difference quotient. Difference in that I'm subtracting two y values, right? Quotient, and then I'm dividing, right? Difference quotient. Yes? It turns out that the limit as h goes to 0 of f of x plus h minus f of x all over h is f prime, the derivative. It gives me the slope of the tangent line. It's a function that gives me the slope of the tangent line. All right, let's take a look. So I'm using Desmos, hopefully. And I'm going to put in a general function. So when you do your version, you'll be able to change everything just by changing the function. Okay? I'm going to pick a specific point on my function as my x, f of x. Okay? I mean, I can keep it dynamic. I guess maybe I should keep it dynamic. Let me keep it dynamic. So I'm going to pick the point a comma f of a. And I call a slider. So I'll allow a to change. I can change it by changing the slider. I can change it by dragging the point itself. I want to create a second point that's x plus h, right? So, and I'm going to actually use that. I'm going to use a plus h. I know it's a little confusing, but Desmos knows x is every point. I have to pick a different letter to get a specific point. So I want a plus h, comma, f of a plus h. And I've got a slider h. If I move my point A, h moves with me. So once h is fixed, right, you can see the distance between the 2 points in the horizontal is 1, right? So again here, the distance between the 2 points in the horizontal is 1. Do you agree? Yeah. If I change h, and that's fine, h will move by itself. But if I move a and h is fixed, it's going to move both points. I want to connect these 2 points to get my secant. So I need to connect those 2 points to get my secant line. So the line we want is what? Y minus y sub 1 equals m times x minus x sub 1, right? And so for us, this is f of x. This is f of a, right? Sorry, that's a minus. Equals m times x minus a. And I guess I'd better define M, right? Which is f of x plus f of a plus h minus f of a all over h. So I'm going to put that in here when I do my dynamic line. This is, I know this could be a little confusing. And I want you to build this on Desmos, right? Okay, you ready? I'll come back to this page, but we need a minute. It's fine. I don't care. I'm in no rush. I'm Polish. I'm not Russian, I like to say. And it's even funny if you're Russian. If I'm Russian, but I'm not Russian. That's even funny. Here we go. F of x. And by the way, that's x squared, right? But if I change my function, everything will change, right? F of x minus f of a equals m. M is this complicated, horrible thing, right? F of a plus h. Yes, exactly. Yep. Oh, sorry. F of a plus h. Oops. I'm having a hard time here. Minus f of a all over h. Oh, damn it. Oh, I did undo. Oh, I did it again. Times x minus a. I did something wrong. Oh, I know what I did. I want that to be a y, not an f of x, sorry. You want me to do this, buddy? You can't even do it. There it is. I don't like red for my line and my graph. How do I change that again? Oh, yeah. There it is, my dynamic secant line. If I move A, my secant line moves. If I move H, right? Now, we're interested in this at a specific point, right? We're interested in this at a specific point. So, for example, at 0, 0, I'm interested when A is 0. When A is 0, oops, here it is. I'm interested in what happens to my secant line as both points move together, right? So I'm calculating this slope is almost 1, do you agree? I mean, if it went from here to here, it's 1, right? Yeah, so it's less than 1, right? And as I move that point H, as I move my 2 points closer to each other, you can see my slope is getting smaller, right? Less steep, yeah? And can you predict for me what the slope of this green line will be when this point is exactly that point? 0. That'd be a horizontal tangent line. Slope of 0, any horizontal line is 0. All right, so that leads us to our problem in homework 4. Yes, yes. Oh, scroll down. Oh, on the left side. Yes. And it's missing something, yes? Let me see if I can get it in there. So this particular thing, when h goes to 0, is going to become f prime. This is going to be our derivative. Right now, this is my secant slope. I'm interested in when h goes to 0, that's my tangent slope. All right, let's look at the problem that they gave us. You don't care if I do some of your homework for you, do you? Do you need me to go back to Desmos? I'm sorry. Don't let me. Let me go too fast. I'm not in a rush. What do you think would happen when it snows? Do you think we're going to have a snow day? Do you think we're going to be remote? Doesn't that suck? No more snow days for the rest of your lives?
Would you mind going back to where we were taking notes earlier?
Sure. Sure. Right, so I remember I picked the points and then I changed it to x plus h and x. And I got this corner, that's my difference quotient. Right here it is again. But this is the equation of a line, right? Y minus y1 equals n times quantity x minus x1. It's fuzzy a little bit. Let me see if I can get a better zoom. Is that better or worse?
I wanted to change it.
Say again?
I'm okay.
Okay, good. All right, let's look at an actual problem here. So this is in homework 4. Sorry. The first problem is just asking you to calculate a bunch of secant slopes, right? Calculate t is 36 and 42. So calculate the slope between these 2 points, right? And then these 2 points, right? You with me? And then these 2 points. And you're trying to predict what's going to happen exactly at 42. Right? Does that make sense? So I'm going to use a bunch of secant slopes, and that slope should be obviously getting closer to a number. Then I want to say, what would be that particular number of heartbeats right at 42? And you can see it. I mean, mine's got it calculated. 67.8, 66.8, 66.5. Where does it look like it's going to? I mean, I would guess 66, but, right? So we'll do one from the other side and see if that's getting to 66. Right? So we're doing this slope, this slope, this slope. Got it. Looks like it's getting closer to 66 to me. And then we're going to do this slope. Let's see. So you know, this side is getting smaller, right? See if the other side is smaller than what I think it is, and then guess what it is. But that's not the interesting one to me. The interesting one is the second problem. So you can see we have a function x over 1 plus x, right? We have a function x over 1 plus x. And we have a fixed point, 1 and 1/2. So we're interested in the tangent line at that fixed point. And what we're going to do is use secants to predict, okay? So let me write the picture down, okay? Now the only thing that's going to change, notice the things that are in red. When you open the homework problem, the numbers in red will change. Someone might have a 2, someone else might have a 3, or whatever. You see what I'm saying? So, but let's use this particular function. I have f of x equals x over 1 plus x. So this is homework 4, number 2. And I have f of x equals x over 1 plus x. I don't quite know what that function looks like, so I'm going to graph it. And wherever I can, I'm going to graph the function. Whenever I don't know what it looks like, I'm going to graph it. So what was it? Y equals, y equals x over 1 plus x. So there it is. And I had a fixed point of 1, 1/2. First of all, do we agree that if I plug in 1, I get a height of 1/2? Do you see that right away? I'm interested in my tangent line at that point. Right? I'm interested in that tangent line. So I'm just going to do a free sketch over here, right? I forgot what it looked like already. Brain like a sieve. There we go. I'm interested in that tangent line, yes? Yeah, you with me? So I definitely should guess a positive number, right? It's pretty obvious that it's positive. And the way I like to figure these tangent lines is picture me skiing on a hill, right? A snow-covered hill, yes, we all understand skiing. And so I'm skiing, I'm standing on that particular, these are my skis, and I want to be able to calculate the slope of my skis at any point on the hill. Right? This is the bunny slope, obviously. So what I want to do is I want to pick an arbitrary point on this curve. And so what should I call that arbitrary point? So I'm going to get a secant out of this arbitrary point. Yes, you with me? So what should I call the arbitrary point? What variables would you use for a point? X, y, good. But we know something about y, don't we? What's y? It's x over 1 plus x, right? It's the function. So we're going to get our secant slope. M equals. I like to keep my arbitrary piece first. So I want to do x over 1 plus x minus 1/2, all divided by x minus 1. Make sure you're with me there. I've got that fixed point of 1, 1/2, right? And I've got my arbitrary point of x, decibel. We're going to do this limit as x goes to where? Where's the interesting value of x from? 1, yeah. And remember, that's the point on the graph where the tangent is. So if I can do this limit as x goes to 1, I get the slope of the tangent line. So how do we learn to do these limits already? Yeah, LCD, what is it? Almost. Right, I'm looking at all the interior denominators. So there's a 2 and there's a 1 plus x, we agree? Yeah. I don't need to do anything downstairs because nothing clears downstairs, right? You see what I'm saying? So I leave downstairs alone, but upstairs things will clear, right? I'm going to x times a 2 times a 1 plus x over a 1 plus x minus a 2 times a 1 plus x over a 2. Where are you? Oh, you're talking about my next line? Oh, yeah. Yeah, so these are gonna cancel and these are gonna cancel, right?
No, he's talking about the main, like the whole thing, the border, the base of the project.
Yeah, the base of the original fraction is x minus 1, right? The denominator, you're saying?
X minus one, and then this goes to the.
Yeah, but there's no interior denominators here, right? This is a denominator, but I don't care about the whole denominator, only the interior denominator. The denominator is within the numerator and within the denominator. That's just two these things. So there's my LCD over itself, so I can multiply by 1. Now I'm simplifying, so what do I get upstairs? I get a 2x minus a 1 plus x, all over 2 times x minus 1 times 1 plus x. Now I'm back to polynomial over polynomial, right? So it looks like I get an x minus 1 over 2 times an x minus 1 times a 1 plus x. This is still my secant slope. Can I plug in the 1? No. Can I plug in 0.5?
Yeah.
Can I plug in 0.9? Can I plug in 0.999? And the computer's going to ask me to do that so that I'm getting secant slopes. But when I plug in 0.5, what does this become? Negative 0.5. What does this one become? Negative 0.5. Don't they cancel? Okay, so I can still use this thing. I can still use this limit, right? Of 1 over 2 times 1 plus x. I can still use this to calculate my secant slopes. I can put in 0.5 there, I can put in 0.9 there, I can put in 0.99 there. But because I did my replacement function, because I cheated, I taught you two limits before I taught you the secant tangent problem. I can just plug in 1 now, and what do I get from the tangent one? 1/4. So the tangent slope is 1/4. And it's kind of nice because I can get the equation of a line here. I get y minus 1/2 equals 1/4 times x minus 1. Right? Make sure you see where I'm getting that from. This is just my equation of my line, right? I need the fixed point, right? 1, 1/2, right? And then there's my slope. So I'm just going to put that in right now as it is into my decimals. I'll come back to this if I'm rushing you. I'll come back to it. Y minus, what did it say? 1/2 equals 1/4 times x minus 1. There's my tangent line. Right, there's that green line. Right? The purple is my secant. As I move those 2 points closer and closer to each other, I'll get the tangent. Let's look at the homework problem again. So what's it saying to do? Get that secant slope for me, which I got for you. Right? Plug in 0.5, plug in 0.9, plug in 0.99. On your calculator, of course, don't do it all by hand, please. 0.9999, gas station money. Can you see where it's going? Yeah? 1/4. 0.25, right? I don't like that they do 0.5 and then 0.9 and then 0.9. I mean, who cares about 0.5? It's nowhere close the pattern, right? You see, once I start doing a pattern that makes sense, I can, look how way off that one is, right? And then they do it from the right. Now, remember what I did. I took my secant slope and made it into a limit, right? And then I evaluated that limit with my replacement function, which, by the way, is called what? What do you think that replacement function is called? What's the name of this guy right here? What's the name of that replacement function? I said it already a couple times today. I said it today, I said it last class. Begins with a D. This is your derivative. And that's what we're learning, we're gonna be learning how to do derivatives. Chapter 3, how do you do a derivative? I'm gonna teach you next week. So, I've already taught you. Take your secant slope and evaluate it as a limit, right? And you know how to do limits, right? Right now we know how to do limits algebraically. Let's see, why don't we do it? What time is it? Ah, damn it. I'm out of time. I wanted to leave a little early, so we're done today. Have a great weekend. Get some work done.